Let's look at another problem about finding the volume of a solid using a double integral. This one's a little different because it's enclosed by a parabolic cylinder, y equals x squared. Notice it doesn't involve z, that's why it's a cylinder. That's the green that's shown over here. And it's having some trouble rotating, unfortunately. And the plane z equals 3y, which goes up in the y direction, and with slope 3, and then z equals 2 plus y. That's the blue on top here. Probably the fact that I'm trying to record this at the same time it's going around is why it's getting confused. Let me try and... Whoa. Eventually it's probably going to stop and settle down. Hopefully you can get a sense of that the green sides and the blue top, and then if you see the underside, I haven't shown you that yet, that's the plane z equals 3y. So the way they suggest to do this in the book is to do it as the difference of two volumes. Right now we only have a tool that gives us the volume of a region whose floor is exactly a region in the xy plane, not some tilted or curved floor. But what we can do is we can take this region. This thing is still getting really weird. We can take this region and think of it as everything under the blue down to the xy plane, and then minus, I guess it's acting as if I've clicked on it, even though I haven't clicked. Okay. That's the underside there, yeah. So you can see that's a side view. We're going to take everything under the blue top minus everything under the red bottom. And so that's going to be double integral over the region D, which we still have to figure out, of the top surface, which is the 2 plus y, dA, minus the integral over that same region of 3y dA. And as with the area between two curves in BC Calc, we can actually just combine that. That's, 2 plus y minus 3y. Or in other words, 2 minus 2y. Oops. But we still need to figure out the setup. But with this picture, whoa, I don't know why it does that. We can see, I think it's upside down now or something. Yeah, I flipped it upside down. I'll have to figure out how to make that interact better with the video. Oh, there we go. That's what you want to be looking at. The picture shows that those two surfaces, the two planes, intersect when 3y is equal to 2 plus y. Okay, so as usual, we're taking each of those equations we're sort of making two of them active, z equals 3y and z equals 2y. So we can set those equal, and we get y equals 1. And so that's going to be that edge, y equals 1. And so the floor plan, I'd love to be able to, oh, actually, you know what? What I'll do is I'll just use the manual control here. Let's to view, I think it's 090. There we go. There's the view from the top of this thing. And so that's going to be bounded by y equals x squared and y equals 1. And so that means it's not too hard to set this guy up. It means that x is going to go from minus 1 to 1. Y is going to go from from x squared to 1. And there's our integrand 2 minus 2y. And that's going to be dy dx. You could do it dx dy, but you'd have to do a square root, and it'd be a little uglier. And one other thing we can observe is that this is symmetrical. Not only is the floor plan symmetrical, but the whole region is symmetrical. It doesn't buy us a lot, but it's kind of a nice thing to observe, and it's always good to practice looking for symmetry, because sometimes it can have a dramatic simplification effect. And we can also take a a 2 out. And so that's probably going to be our simplest way to set it up. And I won't go ahead and finish it off because it's pretty easy from there.